This is the beginning of the differential equations topic for further maths. But it's not the first time you've seen differential equations. You've in fact already learned how to solve a specific type of differential equation during your ordinary A-level maths course. The type of differential equations you've already learned how to solve and the sort we're going to be investigating today are both first order differential equations. First order implies that the highest derivative that appears within your equation is the first derivative, so dy by dx typically. And we use first order to distinguish from second order differential equations primarily, because you will also learn how to deal with some of those later on in this same chapter. In fact, anything that involves derivatives no higher than the second derivative of y will be second order differential equations. Even within these two categories, first order and second order, there are a bunch of other different ways of describing the types of equations you'll be dealing with. And there are some subtleties involved, so it's not always obvious exactly what type you're looking at. And just like with integration, there are often different approaches that you might need to take depending on the exact setup of the equation. So you need to be able to look carefully at what the equation appears to be, think about different ways to rearrange it and rewrite it, and then select the most appropriate method for solving it. Now, you might need to go back and recap. If you are a little bit rusty on differential equations, you'll want to look at chapter 11 from year 2 pure maths. There is a video on this topic, so if you need to, you can go back and look through that as well. I'm going to give a very brief summary of the notes that were in that video, so if you look through it and you feel confident with it, then you can happily carry on. But if you look through and think, well, that was all rather confusing, or I now realize I'm a bit rusty on that, you'll be able to go back, find the original video and recap. So initially we talked about what makes an equation a differential equation, the fact that it involves derivatives, and the other strange thing about it, which is that the solution to an ordinary equation you might think of as being a number or a set of numbers, but the solution to a differential equation is itself an equation or even a set of equations. So we can see here, for instance, y equals x cubed over 3 minus 2 to the x over ln2 minus cos 3x over 3 plus c. That suggests that there's a whole range of different valid equations that satisfy the differential equation, which makes sense because we already know that if you have something like dy by dx equals x squared, there's more than one valid thing that y could be. Y could be x cubed over 3 plus 7, or x cubed over 3 minus pi, and so on. So we use a constant of integration to represent that. We looked at an example as well of how we can solve a differential equation, but this particular differential equation is more complex than just a straightforward let's integrate both sides, because it has y as well as dy by dx. Fortunately, in this case, it was possible to rearrange and separate the variables. So that was the method we worked through here, where you rewrite things so that everything involving y is on the same side and everything involving x is on the other side, including the dy on the side with the y's and the dx on the side with the x's. Once you've done that, you can integrate both sides effectively with respect to whatever the thing is that you've got on that side. We looked at a slightly more efficient way of thinking about it, because in reality you're not multiplying by dx so much as integrating with respect to x, but it works out to give the same thing. So it makes for a nice efficient method, and you want to make sure you're comfortable and confident with that process of solving using separation of variables, because it is an integral part of the differential equations approaches that you might need to use. There are all sorts of equations that might look quite complicated. They might involve some sophisticated integration techniques, but the initial step may well be separation of variables in the same way that you needed it for year 2 pure maths. The other thing we want to briefly mention is the distinction between a general solution and a particular solution. In general, the general solution gives you all the possible curves that satisfy the equation, and they won't necessarily have a plus c involved, because depending on how you solve it, the plus c might end up somewhere else when you rearrange to make y the subject. The particular solution, on the other hand, is the precise curve that satisfies the additional conditions that have been put on it. So if we know the x and y coordinates of a single point on the curve, then we're no longer looking at an entire family of different curves. We're looking for the specific curve that goes through that point. This is a good way to represent a family of curves. If you have a general solution, there'll be some constant in there. And it may be that it is simple as some sort of vertical translation. So the curve looks identical but is shifted up or down. But often the constant is something more complicated. And in this case, the constant represents a vertical scale factor. So you can see a few examples of a times x e to the minus 1 over x. Each of those curves is a vertical stretch from the other ones. And there's no way to know which is the correct one until and unless you're given specific boundary conditions or initial conditions, a particular point that the curve has to go through. Once you've got that, you can identify which of these infinite possible family of curves is the particular solution that you need. You should now be able to have a go at the first couple of questions from exercise 7a in your Core Pure 2 textbook. These all rely on the separation of variables method, so they'll provide some good revision for you for this particular technique, which hopefully you do mostly remember from A-level maths last year. So we now know that if we have a differential equation that looks a bit like this, a function of x multiplied by a function of y, or one that we can at least write in that form, then we can separate the variables and solve directly by integration. However, most differential equations that you come across, even first order differential equations, which is the sort we're focusing on at the moment, can't easily be solved in that way. Even ones that look relatively straightforward might simply not be in that form, two functions multiplied. They might look straightforward, but we're going to need some other technique, another trick to tackle them. Take a good look at these three examples and see if you can spot a common pattern, some feature within them that we might be able to exploit. And your clue for this is the title of the section. Have a little think, pause the video, give it some thought, see if you can come up with an idea for what's going on. When you're ready, unpause and continue. With a bit of color coding, perhaps you can see more clearly what the underlying structure is here. In every case, if we focus on the left-hand side of the equation, we have a function of x and then dy by dx, and then we get another function of x and y. But not only that, the second function of x is the derivative of the first function of x. So if we have sine x times dy by dx, then over here we're going to have the derivative of sine x multiplied by y. Over here we've got x cubed and then 3x squared. Even on the first example we've got an x and then 1y. So the derivative of x is 1. You might recognize this particular format, particularly the very first equation there on the left, from implicit differentiation. If you have to differentiate two terms multiplied together implicitly because they involve x and y, you will typically end up with this type of result because you have to use product rule. Have a go with these three expressions, take each one separately and differentiate them with respect to x. You'll need to differentiate implicitly because they involve a function of y as well as a function of x. And you'll need to use product rule because each of them is the product of two functions. When you've managed to successfully differentiate them, you should recognize how your results will come in handy for dealing with the differential equations above. And I recommend at this point you have a go at solving those differential equations using what you've noticed. The more you can create this idea for yourselves, the more it will stick in your head and the more easily you'll be able to notice it and apply it and use it in later questions for yourselves. So let's rewind a little bit and think more carefully about what we mean when we talk about reverse product rule. In general, if we have a differential equation that looks like the three examples we saw on the previous slide, f of x times the derivative of y plus f dashed of x times y on the left hand side, then because that perfectly matches the format of product rule, we could do the opposite of product rule and generate for ourselves in one easy step the integral of the left-hand side. So if we want to integrate the left-hand side, of course, we would also need to integrate the right-hand side so that we have the same thing happening to both sides of our equation. But because of product rule, we already recognize the left-hand side as being the result of differentiating f of x times y. Remember, when you use product rule, we have uv differentiating the uv dash plus vu dash. So each term stays the same or gets differentiated in turn. F of x times y will give us f of x times the derivative of y plus y times the derivative of f of x. Which means when we go in reverse, as long as we've got this format matching what we've got on the screen, we can integrate it and turn it into simply f of x times y. On the right-hand side, we just need to integrate whatever we had already on the right-hand side. So let's look now at the three examples we had on the previous slide and work through piece by piece to see how this approach solves those equations. These were the three that we had: x dy by dx plus y equals 2, etc., etc. Each one already fits the format that we need. There's no need to do any rearranging. We can identify the f of x in each case. For the first one, for instance, f of x is just x, and f dashed of x is 1, so we have 1 times y. For the second one, f of x is sine x, and the third one, f of x is x cubed. So we can move straight to the next line. When we integrate the left-hand side, we can simply do the opposite of product rule, and we get left with xy, or sine x times y, or x cubed times y. And that's really nice and elegant, and you'll get very quick and efficient at that process when you practice it a little bit. As soon as you've got the left-hand side in the correct format, you can basically shortcut the entire process of integrating it and jump straight to the opposite of product rule. You're going back from whatever product rule would have given you to whatever you would have started with. Of course, because that process allows us to integrate the left-hand side, we also need to integrate the right-hand side. But that's relatively quick depending on the function you're dealing with. 2 integrates to 2x, e to the x integrates to itself. Tan x is one that you might need to look up, but it is one of your standard results. So as long as you know that it's one that will be in the formula book, you can just go straight to the formula book and pull out the result you need. In every case, we've got a plus c. This is particularly important. It's worth remembering that the process of solving a differential equation is essentially the next level on from just integrating an expression. And just like with integration, there'll be a constant of integration. We'll have a plus c when we've finished integrating, and that c gives us a way of describing the entire family of valid solution curves. The last step is usually to rewrite in terms of y, if possible. Generally, it's possible for this type of equation. We end up with y equals 2 plus c over x for the first one, y equals e to the x plus c all over sine x, and then y equals ln of sec x plus c all over x cubed. You'll notice, including the very first one, if we'd ignored the c, we would have found a trivial solution. Y equals 2 is a perfectly valid solution to this if c happened to be 0, for instance. Y equals 2, if we differentiate y, we get dy by dx equals 0. So we'd have x times 0 add y equals 2. So it works. But more generally, there is an entire family of curves. Anything which is a y equals something over x plus 2 would also satisfy this differential equation. So including the constant doesn't just give us some kind of, oh yes, and you can move this curve up and down. It gives us the additional dimensionality to describe all of the possible curves that satisfy this particular differential equation. For the second one, you can see the plus c gives you an extra constant on the top of the fraction, and the same with the third one. But in both cases, it's not just added to the end of the function. It's not y equals something plus c. It's sort of embedded within the expression, which means that changing the value of c will give you a somewhat more sophisticated transformation of the curve. If you're curious, I recommend you type this into GeoGebra or something like that. If you use a k instead of a c, then GeoGebra will automatically pick that up as a constant that might want to change. So it'll give you a slider, and you can mess with the slider and observe the different curves that you end up with. Very often, they're more interesting than what you would get if you were just moving a curve up and down. But every single one of them within the family will satisfy the original differential equation. Now you should be able to have a go at the question 3 from exercise 7a. The first 4 parts of this question are pretty much exactly the same type as these 3 examples. The equations are given in the appropriate format, and you just need to identify which bit is your f of x, and then do the integration from the right-hand side, rearrange, and you're done. For E and F, the principle is the same, but the execution is somewhat different. So you've got to look carefully at what's going on, and it won't match exactly what we've got here with f of x dy by dx plus f dash of xy, but it will still be something where you can take advantage of the idea behind the reverse product rule. So those are particularly good ones to try and think carefully through. You'll understand better the overall process having done parts E and F. Now, you may be feeling a little bit skeptical about the power of this method, the reverse product rule method, and you'd be right to be suspicious because it doesn't seem that likely that a randomly generated first order differential equation will allow itself to be written in the form of the reverse product rule. Having each term exactly fit the format that we require seems a bit fortuitous. And that's kind of correct, but it turns out that for a fairly broad general family of differential equations, it is possible to rewrite in the form of reverse product rule. So it turns out to be quite a powerful technique, but it can be a little bit fiddling to get the differential equation written in the format that we need. Let's take these 3 as examples. If you look carefully, you'll notice that although they might look on the surface like classic candidates for reverse product rule, x to the 4 does not differentiate to give 3x cubed. Tan x does not differentiate to give 1 for part B, and e to the 2x does not differentiate to give e to the 2x in part C. So we have a few issues. However, if you are clever, you can multiply the left and the right-hand sides of the entire equation by some function which transforms it so that it will be in the reverse product rule format. Have a little think about exactly how the 2 functions that we've currently got are related, and see if you can come up with a way of multiplying both sides of the equation, which will involve both of the terms on the left-hand side, by something, or potentially dividing by something, because that's effectively the same, mathematically speaking, but it might be easier to look for what can you divide by, or what can you multiply by, to convert these equations into equations that can be tackled using the reverse product rule technique. If you manage to find out, then the next step is to solve the differential equation. Once you've got it looking like reverse product rule, then find the general solution to the differential equation, and then also find the particular solution. And we're going to use the same set of boundary conditions for all 3 of these. So let's assume that the curve goes through the origin, the point 0, 0. Pause the video, have a go at those 3 questions, see how much headway you make. I would highly recommend you work through and you look for the term that's going to work for these on your own before you skip ahead and look at the answers, because the more you do for yourselves and the more you make sense of and struggle with, the better it will stick in your head. It'll be something that makes sense to you because you tackled it and solved it on your own instead of just waiting to be handed the solution. When you're ready, we'll go through the answers together. Okay, in the first question, part A, the trick here is to notice that we've got a 3 in front of the x cubed. I can think of something that differentiates to have a 3 in front when the original doesn't, and that will be x cubed. So if we had x cubed instead of x to the 4, and we had 3x squared instead of 3x cubed, then it would fit the product rule idea. And we can do that. We just need to divide both sides by x. You'll notice on the right-hand side we already had an x term, so that's convenient because that will cancel out as well. That will give us something on the right-hand side which will be easier to integrate when we get to that step. With part B, this is somewhat sneakier, but if you were stuck and you were staring at it for ages and you couldn't figure out a way through, I wonder if you thought of turning tan x and sec x into their more fundamental component building blocks, sine and cos. If you do that, you might find it easier to see what term you could multiply or divide by to make this work better. Tan is sine over cos and sec is 1 over cos, so perhaps it will be simpler if we multiply through by cos x, and if you do that, we get a sine and a cos, and of course cos is the derivative of sine. Not only that, but the right hand side has turned into something even nicer. So although you could integrate sec, you'd need to look it up in the formula book, we can integrate the number 1 even more easily. The last one, e to the 2x, doesn't differentiate to e to the 2x, but e to the x differentiates to e to the x. So by dividing through by e to the x, we are able to turn this one as well into the reverse product rule format. Once we've got them all in the reverse product rule format, the next step for each one would be to reverse product rule. We need to look at the terms we've got, identify what the undifferentiated terms within there would be. So for instance, if we were differentiating with product rule, we write down one term and multiply by the derivative of the other, and then we write down the other term and multiply by the derivative of the first. That means that the two terms that we would have had originally will be x cubed and y. X cubed times y, when you differentiate it, will give x cubed dy by dx and 3x squared times y. So x cubed y. On the right hand side, I've already integrated as well. The integration step for the left hand side is essentially using inspection to recognize our left hand side as the result of product rule and then reversing that to get the original product that you would have had. On the right hand side, we integrate. Sometimes it's nice and simple, sometimes it's more involved. In this case, cos integrates to sin x. And don't forget the constant. If you don't have the constant plus c, then it's mathematically equivalent to assuming the constant is equal to 0, and you'll be finding a particular solution, not necessarily even the one that we want, but it would be a particular solution rather than a general solution. So you wouldn't get the marks for the general solution, and you also would struggle to then find the particular solution later on if you're given additional conditions, because you won't have a c to calculate the value of. We can also simplify that as the question required, and all we need to do there is divide by x cubed. And you can see that this is why the c that's added on doesn't just give you translated versions of the function, but it's going to add multiples of 1 over x cubed to the function, which complicates the transformation somewhat. For part B, inspection with reverse product rule gives us sin x times y. Again, you'll see that's the first term over on the left and the second term on the right hand side of the left hand side. So of the 4 terms you see on the left hand side of the equation, the term multiplied by dy by dx is the undifferentiated x term, and then y is the undifferentiated y term. So they're the only 2 pieces we need. We get sin x times y. And on the right hand side, don't forget to integrate, we'll get x plus c. And that of course simplifies when we divide by sine. For the last one, e to the x is the term that gets differentiated to give e to the x, and y is the term that gets differentiated to give dy by dx. So we have e to the xy when we reverse product rule. And on the right, if you integrate e to the 4x minus 2, you will get a quarter e to the 4x minus 2. Exponentials integrate and differentiate to give the same exponential function, give or take some scaling factor that will be determined by the power within that function. So if you have e to the power of 7x squared, if you differentiate it, you'll end up with e to the power of 7x squared multiplied by 14x. If you're integrating, it's a little trickier. You need to have something linear in the power if you want to be able to use reverse chain rule. But in this case, it is linear, so we can just multiply by 1 over the derivative of 4x minus 2. And don't forget the plus c. And final step here will be to divide by e to the x. And I'm going to incorporate that by putting c e to the minus x. But there are other ways to write that as well. So these are our general solutions. The next step is to look for particular solutions. And for part A, we have to substitute 0, 0 into our equation. Remember, we know that the curves go through the origin. So if we make y equal to 0 and x equal to 0, we can solve to find c. Now I'm using this version because you actually lose a bit of information if you are forced to rearrange to the form y equals something. Because there's nothing about the original curve equation, albeit it's an implicit function, the way it's written rather than explicit, but x cubed y equals sin x plus c is a perfectly valid function to evaluate when x equals 0, even though the rearranged version would struggle when x equals 0. So I'm going to use the unrearranged version to find c, and it turns out that c would equal 0. X cubed y is 0, sine of 0 is 0, so c is also 0. And then we'd simply rewrite the general solution with the appropriate value of c included in it. The same thing happens for part B, and again c comes out to be 0 when we replace x and y with 0, and so our particular solution is y equals x over sine x. For c, however, don't get complacent, because c is not necessarily always 0, especially when you've got trig or exponentials around. You have to be very careful with this. When we replace x and y with 0, on the left hand side over here we'll have e to the 0 times 0, so 1 times 0, so the left hand side is 0, but on the right you get a quarter e to the 0 minus 2, so a quarter e to the minus 2. And when you rearrange, that means c has to equal negative a quarter e to the minus 2. And then we can substitute that back in. So where we see c in our general solution, we can replace it with minus a quarter e to the minus 2. And when we simplify a bit, we'll get this, a quarter of e to the 3x minus 2 take away e to the minus x minus 2. There are a couple other ways you could rewrite that, but that's about as straightforward as it's going to get. So remember, this is the general solution, all three here, the y equals sine x plus c over x cubed, y equals x plus c over sine x, and y equals a quarter e to the 3x minus 2 plus c e to the minus x. We can recognize them as the general solution because there'll be some constant in there, and changing the value of the constant gives you different curves, but within the same general family of curves, each of which is a valid solution to the original differential equation. And then this will be the particular solution. This tells you the exact curve which not only satisfies the differential equation that we had at the beginning, but it also satisfies the additional condition that you're given, which in this case was the boundary condition that when x is 0, y is 0. Now you should be able to have a go at question 8 from exercise 7a. Using a similar technique to these, look carefully to see what you could multiply or divide both sides of the equation by to convert it into a format where you can use product rule. Now we're going to look at an example of a differential equation that on the surface looks really straightforward, but when we start thinking more carefully about it, we realize we're going to struggle to solve it. dy by dx equals x plus y. Now you've solved differential equations that look complicated, and this one doesn't. It looks really straightforward. You would think if we can solve a differential equation with dy by dx equals x times y, and we can solve one with x times sine of y and all these other complicated things, surely x plus y shouldn't be that hard. But the variables are not separable. We can't just divide through by something and get all the y's on one side and all the x's on the other side, because we don't have a product of two functions there. We've got the sum of two functions. So what can we do? Well, perhaps we can rewrite so that it looks a bit more like the versions we've just been looking at, the reverse product rule problems that we've been dealing with. We have dy by dx minus y equals x. However, you can see that the number in front of dy by dx, in this case it's just a number, not even a function, but a constant. It's 1 times dy by dx and minus 1 times y. 1 doesn't differentiate to give minus 1, so it's not in the reverse product rule format yet. But if there is something we can multiply by to make it the correct format, that something would have to be a function that fits this condition. It would need to differentiate to give the negative of itself. So is there a function that when you differentiate it, you get the negative of itself? And these are somewhat abstract next level questions about functions. We're not saying here's a function, differentiate it. We're saying can you come up with a function which satisfies this particular condition? There are functions that you've looked at already where differentiating them repeatedly gives you something of a similar level of complexity to the original function. Polynomials don't work like that, but if you had something like a reciprocal or an exponential or a trig function, you'll find that differentiating them doesn't ever get you down to constants or zeros like it would if you differentiated a cubic. It's going to become quadratic, and if you do it again, you get linear, then constant, then zero forever. But there are some functions that are complicated enough that they don't do that. And perhaps while I've been talking, you've been thinking and you've come up with a function that differentiates to the negative of itself. It's very similar to the idea of a function that differentiates to itself. So that might have been somewhere in the back of your mind. E to the x is going to crop up a lot while we're dealing with differential equations, simply because it has that really, really useful property that when you differentiate it, you get e to the x, the same function you started with. It is the fundamental solution to the equation dy by dx equals y. So it's a really useful function to have at the forefront of your mind when you're trying to solve differential equations. And in this particular case, a slight modification will make this work. We try e to the minus x, because when you differentiate e to the minus x, you get minus e to the minus x. So let's try it. Let's take this factor e to the minus x and multiply both sides of our original differential equation by e to the minus x. Now we have e to the minus x dy by dx minus e to the minus xy equals x e to the minus x. Don't forget you're multiplying the right-hand side as well. Our focus is on the left-hand side because that's the one we're trying to turn into the correct format, but don't forget that there is a right-hand side, so you've got to make sure you incorporate anything you multiply both sides of the equation by. You've got to include the right-hand side, of course. The next thing we can do is the reverse of product rule. It's in the correct form, so we can integrate. And when we integrate the left-hand side, we don't even need to perform an integration. We just need to observe by inspection that the integral will be e to the minus x times y, because it's already in the product rule format. On the right-hand side, however, we do need to perform an integration. And this is a non-trivial integral to calculate. The integral of x times e to the minus x. Crazy that there's exponential terms in there, because the original equation dy by dx equals x plus y didn't give any hint that there was going to be some sort of e to the x component in the solution. But that's often the way with these things. Any equation that is a differential equation that involves dy by dx as well as y is likely to have, hiding behind the scenes, something involving exponential functions because of how fundamental they are to the entire nature of functions being related to their derivatives. Now, if you had to integrate this function on the right, there is a standard technique you can apply. Hopefully you remember it. If not, pause the video and give it some thought to see if you can think of what technique you would use in this particular case. Hopefully you have come up with integration by parts. We're looking at a classic example of two things multiplied. You need to integrate two things multiplied together. And while we're talking about product rule, integration by parts is essentially what you get when you integrate both sides of product rule. And so it's a sensible way of dealing with the integral of a product. But if you remember, product rule is a way of differentiating directly. If you've got a product, you can differentiate it and get the derivative. Integration by parts doesn't do the integration for you, but it allows you to turn the integral into a different type of integral. And hopefully the different integral you generate will be easier to deal with directly than the one you're currently dealing with. Let's move on and look at how we can integrate this by parts and then incorporate it and finish this whole example. So we've got to the point where we have e to the minus xy equals the integral of x e to the minus x, and we need to use integration by parts. So the first thing we do is write down the parts formula. It is provided in the formula book if you need it. The integral of u dv by dx is equal to uv minus the integral of v du by dx. You can see the hints of product rule hiding in there. It's essentially a slightly rearranged version of the integral of product rule. But now that means we need to identify which bits in our integral will be u and dv by dx. And this choice is generally made for us. We look at the integral, and unless you've got ln involved, we normally choose the bit that's going to get simpler when you differentiate it to be the bit we differentiate. In other words, u. So we'll set u equal to x, and we'll have dv by dx, therefore will be e to the minus x. When we differentiate u, we get 1, and when we integrate dv by dx, we get minus e to the minus x. Then we substitute those back into the parts formula, and we can see that our integral is going to give us uv minus the integral of v du by dx. So we know u and v, that's x and minus e to the minus x. We know v and du by dx, it's just minus e to the minus x and the number 1. So by rewriting our integral in terms of this new integral, we actually have a simpler problem to solve because our integral no longer involves a product. We can integrate minus e to the minus x with respect to x, and we'll generate our result. It'll actually be a positive e to the minus x. And we're taking that away, so this is our integral. This gives us the general solution. Come back to look at the original equation we were solving. We had e to the minus xy equals the integral that we were working on over there. So now we'll replace that integral with minus x e to the minus x, take away e to the minus x plus c. I've rewritten it slightly to make it look a bit nicer, but it doesn't really matter what format you have. What you'll notice, however, for the next step, if we multiply both sides by e to the x, we can cancel out the e to the minus x. That means it entirely disappears from the bracket, but it appears next to the constant of integration, c. So we have y equals c e to the x minus x minus 1. And it's another example, in fact, of a curve which could turn into a trivial example if c was equal to 0. So if you forgot to include the constant c, or if you decided to set c equal to 0 at this point, you would find the equation of actually a straight line that satisfies that differential equation. Y equals minus x minus 1. And you can check that this works by going back to the original differential equation and using y as minus x minus 1. If y is equal to minus x minus 1, then x plus y would be x minus 1, which is just negative 1. And then dy by dx would be equal to negative 1. And that is, of course, true. For the line y equals minus x minus 1, the gradient is always negative 1. So it certainly works with y equals minus x minus 1. But it's a trivial example in the sense that there's an entire family of curves which involve the exponential function, which also satisfy this differential equation. Next, we go to the initial conditions we were given. This is sometimes known as the boundary conditions or initial conditions, but it doesn't necessarily have to be at the boundary or the beginning. It's just some information that we can use to tie down exactly which of this family of curves we care about. Our curve passes through the point 1, 0, so I'm going to substitute 1 instead of x and 0 instead of y. So we get 0 equals c times e minus x, which is 1, minus 1. It gives us a value for c. It's got to be 2e to the minus 1, or 2 over e if you prefer. And once you've got that, we can generate the particular solution. We go right back to the general solution and just replace c with 2e to the minus 1. I've simplified slightly as well, but there's not a whole lot more we can do with that. So that one is our particular solution. And if you're curious, I've shown it on a graph. And as well as the particular solution, which is in bold, we've also got dotted lines to show a few more from that same family of solutions. You might want to think about what the positive and negative versions of this mean in terms of the values of c that would generate them. And you can also see the trivial solution, y equals minus x minus 1, running down there as the straight line in the middle. In fact, another question that is sometimes asked at the end of a problem like this would be to discuss the nature of the function or the long-term behavior of the function as x tends to, say, minus infinity. So for smaller and smaller values of x, even if we're looking generally at the general solution, you could still say something sensible about what happens as x gets lower and lower. If x is minus 10 or minus 100 or minus a billion, what happens to y? Well, you would get c times e to the minus a billion, or c times e to the power of some massive negative number, meaning that that particular term would get smaller and smaller and smaller. And as x tends to infinity, this bit would tend to 0. We get exponential decay as x gets to be a larger and larger negative until that bit essentially shrinks away. And we'd be left with a function which basically looked a lot like just minus x minus 1. And that's why all of those curves converge towards the line y equals minus x minus 1 as x tends towards negative infinity. Now, we move on to the big daddy of this particular topic, something called the integrating factor. This is the really powerful bit. You are not expected in general to need to come up with some sneaky clever method for converting your differential equations in every case. It should be possible to generalize the trick that we did with that exponential term in our last example to come up with a general formula or method for dealing with a whole range of first order differential equations. If we have a differential equation that looks like this, dy by dx plus something times y equals something, where the two somethings are just functions of x, then there should be some function that we can multiply through which would turn that into a reverse product rule situation. Now this is the clever part. We need to find a function that differentiates to p of x times itself, because p of x is the function that is multiplied by y. And in the same way that we came up with f dash of x is equal to minus f of x, that must give e to the minus x, we have a similar thing going on here. E to the something always differentiates to e to the same something multiplied by the derivative of the something. Which means if we want to find a function that'll work here, that'll do the job, multiply through by some mystery function and turn it into a reverse product rule format, we need to pick the function to be e to the power of something which differentiates to p of x. Well, something which differentiates to p of x is equivalent to saying the integral of p of x. So we need e to the power of the integral of p of x. It's a bit of a mouthful, but it's a really powerful idea. It's a powerful value, a powerful expression to use. So it's known as the integrating factor. It's a factor, it's something we multiply through by so that it becomes a factor of the left-hand side, and that will allow us to take advantage of the reverse product rule process. And we'll be able to do it in any situation. Wherever we can write our equation in the form dy by dx plus some function of x times y equals some other function of x, all we need to do every time is multiply through by e to the power of the integral of that function of x that was sitting in front of y. Let's go through a quick example, a generalized example. The differential equation dy by dx plus p of x y equals q of x will get multiplied through by this integrating factor, and I'm going to call it I to make things a little neater here. On the right hand side, yes, we have a slightly different function then, I times q of x. On the left hand side, we have I dy by dx plus p of x times I times y, and that matches the reverse product rule format, because I has been specially designed so that it differentiates to give p of x times I. Just like e to the minus x differentiates to give minus e to the minus x, that lets us take advantage of the link between the dy by dx coefficient and the x and the y coefficient. Here we've got I, the integrating factor, in front of dy by dx, and we have p of x I in front of y. So then we can use reverse product rule, and that just gives us the integrating factor multiplied by y equals the integral of the right hand side. It's very elegant, and although it feels a little bit fiddly when you first begin, and it's certainly a bit awkward to try to write e to the power of the integral of something, it's a really useful result. So let's look at an example using this integrating factor. We want to find the general solution to this equation, and if we look carefully, we'll find that it's going to be no easy task to solve this using straightforward integration. That's not going to work because there's a y as well as x's involved. We can't solve it using separation of variables because there's no way of writing it as a function of x multiplied by a function of y. So we need either to use reverse product rule, if we can see something quick and easy that will do that for us, or apply the integrating factor technique, which will give us the reverse product rule format that we need. It'll take the hard work and clever thinking out of it for us, essentially, and let us deal with it directly, regardless of what those functions happen to be. So first we rewrite it. Now, for the integrating factor formula to work, we need to make sure it's 1 in front of dy by dx. So instead of trying to think of something clever to multiply by, we just divide through by x and then rewrite so we have dy by dx terms, the y term, and then on the other side of the equation whatever's left over, which should be a function of x. So now we have 1 times dy by dx minus 2 over x times y equals x. And then the p of x function, that is minus 2 over x. So we can calculate the integrating factor next by pulling out that function, or that expression there, the minus 2 over x. That's going to be the function p of x that we need to use to find our integrating factor. E to the power of the integral of minus 2 over x. Well, fortunately, minus 2 over x is an easy integration to do, because 1 over x integrates to ln x, and we can keep the minus 2 outside the integral sign for that. So minus 2 lots of ln x. And then we get e to the ln of x to the minus 2. There's a reason I'm pulling that power inside. I'm using the log laws that let me do that. Equivalently, you could use index laws to write this as e to the ln x in a bracket to the power of minus 2. However you do it, we're able to actually simplify beyond just the exponential, and we get x to the minus 2. This is worth noticing. Although the integrating factor is always of the form e to the power of something, just because it has e to the power of something doesn't mean that it will not simplify to something that doesn't involve exponentials. Often you've got something involving logs that appear from the integral, just like happened here, and you can simplify further to the point where you've got a relatively nice function to multiply through by. So our integrating factor is just 1 over x squared. Now we go back to the original, we multiply through by our integrating factor. I've left it in index form on the left hand side because it's easier to see which bit differentiates to what, and I can verify independently for myself that now this is automatically in the reverse product rule format. And on the right hand side, I've treated it as 1 over x squared. So x times 1 over x squared gives me 1 over x. Then we apply reverse product rule. I should say it is possible, once you've calculated the integrating factor, to jump straight to this line. But it's not something that I normally do for a couple of reasons. One is that if I do that, I often forget to multiply the right-hand side by the integrating factor. And the second reason is that if I make a little mistake somewhere, then it's harder to pick it up. If I include that line where I multiply through by the integrating factor, I can independently verify for myself that I am looking at something which is in the correct format. X to the minus 2 differentiates to minus 2x to the minus 3. So I know that I'm looking at a reverse product rule situation. So now we've got that. Reverse product rule allows us to automatically integrate the left-hand side, and then we still need to integrate the right-hand side. Luckily, that doesn't take too long because 1 over x integrates to ln x plus c. The last step we can do here is to multiply both sides by x squared so that we have y equals. And we've got the general solution to the equation. Incidentally, this is what our general solution looks like for a few different values of c. Because c, again, is not just a number that gets tacked on the end of the function, it's something which is effectively adding a multiple of x squared to a curve which would otherwise have just been x squared ln x. It means that the transformation is a little more sophisticated than just a vertical translation. It's also only valid for positive values of x, which you can see if you think about the fact that we've got ln x involved, then that makes perfect sense. A couple of extra points I want to make. The right-hand side is the bit that tends to be forgotten in this. Our focus is on the left-hand side throughout this entire process. Once we've got it rewritten in the required format, the left-hand side is what matters. That's the side we look at when we figure out the integrating factor. That's the side that we apply reverse product rule to. So watch out at this step that you actually do multiply both sides by the integrating factor, and watch out at this step that you actually integrate both sides, because that process of multiplying by the integrating factor is something which you will be focusing on the left-hand side to do, because that's the side we're trying to get in a particular format. You might forget to do it on the right. And then for the integration is effectively done for you by reverse product rule on the left. So you need to consciously remember to apply it for yourself on the right. Now you should be able to try questions from exercise 7a. Any of those questions should be doable. Some of them involve hyperbolic functions. So if you've not yet covered that chapter, you might want to leave those for the time being. Anything that looks like it has a misspelt trig function is something you want to watch out for if you've not done hyperbolics yet. But questions 7, 9, 10, and 16 are good starting points. So I'd recommend you begin with those.